My apologies for that nonsense. I did start 2 minutes before class. It just took us 7 minutes to figure out how to do that. Good grief. Anyway, Heavenly Father, we thank you for this day, and just thank you for these students. Just ask you to help us to glorify you what we do and to understand a little more about complex analysis, Lord. In your name I pray, Lord Jesus. Amen. So let me just remind you guys. Definition. If z is not equal to 0, then and z is equal to modulus of z times e to the I theta, then theta is an element of the argument of z. So this is a set of things. Moreover, arg z is an element of arg z intersected with minus pi not included to pi included. All right. So arg z is a specific fixed value for any non-zero complex number. It is the unique standard angle between minus pi and pi, minus pi not included. And we also defined what? We defined other choices of angle, right? Other arguments. And let me just put them up here so we have them. Need to learn, well, you certainly need to learn this one, but you should be aware that you might need the others for certain problems in order to bring clarity to the question. So the other one we defined was like arg alpha. What was it? Where'd that thing gone to? Guess help me out. Where'd I? Arg sub alpha. Oh yeah, there it is. Page 7 in my notes. So arg sub alpha plus of z is an element of arg z intersected with alpha minus 2 pi not included to alpha. And arg alpha of z is an element of arg z intersected with alpha included to 2 pi plus alpha. All right. So before I do anything else, let's just work a couple of examples to try to understand fully this notation, all right? Like, so one of the key, key identity to understand these calculations that we're about to do is that if we, well, basically just this, e to the I theta equals to e to the I beta implies that theta minus beta is an element of 2 pi I z. All right. So we don't get, I'm assuming here that theta and beta are real. All right, context here, theta and beta real. If theta and beta were complex, then I don't get this. I don't believe. All right, anyway, so that's the issue. It's not one-to-one anymore. We have this, like, another way to look at this is if you have e to the I theta plus 2 pi j, well, that's e to the I theta, all right? For any integer j, all right? So this is the, the fall from one-to-oneness that we just have to face it. It's a good part of what makes complex analysis a little bit tricky in places, but it's not too bad. All right, so example 1. here's one I like, I. Right? So I is equal to e to the pi I over 2. Oh, by the way, I assume that you guys have memorized, have internalized the fact that e to the I theta is cosine theta plus I sine theta. Like, you know this. You should memorize this. This is something you know. All right? So, since we know that, what is cosine of pi over 2? 0. What's sine of pi over 2? 1. So, true. All right? And that tells me that the principal argument of I is equal to pi over 2. Another example. If we had minus 1, I can write that as e to the, I pi, or pi I if you like. Do you trust me? Sine of pi is 0, cosine of pi. So, true, yeah. So yes, yeah. So is the argument pi? Like the argument of minus 1, what is it?
Yes.
Yes. All right, very good. How about arg sub 0 of minus 1? What's that equal to? So we'd be using this guy, trying to pick the angle that falls between 0 and 2 pi not included. Still pi. What if we did arg sub pi maybe of minus 1? What would that be? So this has to be like, what's the, if you, oftentimes I like to think of this as being a theta, and so it's between what and what? By definition, it's between less than or equal to pi and, oh man, let me put a plus up here, that's what I wanted. So, it's still upon me. Rats, I'll forget the plus. It's still, oh man, it's still pi. Oh, that's 3 pi, right? Duh. See, pi, 2 pi plus pi less. So the argument sub pi is still pi. I was trying to make it different. I failed. So you guys, tell me something that'll make it different.
Arg sub 2 pi?
Arg sub 2 pi. All right. Without the plus or with the plus?
Without the plus.
Without the plus. All right. What do we got? So that means it's got to be this, if this is theta, it's got to be less than or equal to 2 pi and less than 4 pi not included, right? So
it's got to be 3 pi.
It's got to be 3 pi, right? Because this is equal to e to the 3 pi I. And so we have to choose the angle that fits in that range. So yeah, 3 pi. There we go. Okay? Not complicated. You just have to think through the notation. Yeah. All right. And more often than not, we're just using the principal argument. All right? Okay, so the other thing I should mention is that e to the I theta to the n is equal e to the I n theta. This is de Moivre's theorem. So this is another handy dandy identity that we know for the complex exponential. We use this sometimes. You can prove this with mathematical induction, right? Now, I'm going to go on here. So, so definition. There really should be like lights right here in this room. This is like my pet peeve in this room every single semester, is I always feel like I'm in the dark half the time. I've actually thought about like coming in and actually installing like a light in front of each board. It makes me sleepy. Anyway, definition. Suppose n is a natural number, and you got z and w in the complexes such that z to the n is equal to w. Then z is an nth root of w. Moreover, the set of all nth roots of w is denoted w to the 1 over n. All right. So let's work out a formula for these. Like, let's understand how we actually find these for a given complex number. And what we're going to do is we're going to use the polar decomposition, and we're going to just work. We're just going to work through it and see how it comes to us. Right. So what we want to do is assume we've got the polar form of z and the polar form of w, and kind of go from there. All right. So we're gonna let w equal rho e to the I phi, and we're going to let z equals to r e to the I theta. All right. So those are the polar forms. So I'm assuming that rho and r are respectively the length, the magnitude, if you will, of z and w respective. All right. And then what are we looking at? Well, we're looking at z to the n equal to w. Right? So z to the n equals to w. Tells me what? That tells me r e to the I theta raised to the n power is equal to, well, rho e to the I phi. All right. But if you have a product of complex numbers raised to the n power, it's true that we have r to the n e to the I theta to the n power. All right? And if you'll believe me that de Moivre's theorem is true, we can trade e to the I theta to the n for e to the I n theta. If it's bothering you guys, we could take a second. It'd take us all 3 minutes to prove this theorem. Let me do it. Let me fill the gap there. That does make a nice test question, so I guess I probably should like be a decent person and show you why this is true. First of all, n equals 1 is clear, right? Because like n equals 1 is just notation. Suppose it's true for n. Suppose inductively e to the I theta to the n is equal to e to the I n theta, right? For some n in the natural numbers, and theta is a real number, okay? Then what? Consider e to the I theta to the n plus 1 power. Well, by definition, that is what? That is e to the I theta times e to the I theta to the power n, by definition of exponent. We define exponents of natural numbers recursively like this. To get to the n plus 1th one, you do the thing times the nth one. That's our definition of exponent. So for natural numbers. Now, the definition of exponent for complex numbers we haven't made yet, and that'll be different. We'll get there. Maybe today. But then this is equal to e to the I theta times e to the I n theta, or n I theta if you like, by induction hypothesis, right? And then we need to use the law of exponents that I claimed was true last class. And since I claimed it was true last class and no one objected, it's now true. So that's proof by lawyering. We use that to, like, you know, keep anyone from objecting to, like, cheating during the voting usually. Like, ooh, yeah, I'm sorry, you can't object now. It's like more than a week after the vote. So, sorry. Ooh. Playing game, I don't know. Like, I do want this video to be monetized, you know? I gotta be more careful about my comments. Could, you know, get me into trouble. Anyway, so there you go, and that is the claim for n plus 1. Therefore, by proof by mathematical induction, de Moivre's theorem holds, right? Current gap in what I've shown on the board is I haven't proved for you the laws of exponents. But again, you can prove those directly from laws of the adding angles formulas for sine and cosine. All right. So now that we got that, let's come back to here. What we got? We've got r to the n, e to the I n theta is equal to rho e to the I phi, right? Now, there's two things we get here. We get, on the one hand, that r to the n is equal to rho. How do I know that? I can take the magnitude of both sides of the equation, right? The magnitude of the left has to be equal to the magnitude of the right. So that gives me that r to the n is equal to rho, because remember that the magnitude of e to the I whatever is equal to 1, right? Although I am assuming that Pac-Man is real. All right. We haven't yet defined the quote-unquote complex exponential. We'll do that soon, but we haven't done it yet. All right, so we on the one hand get that, but on the other hand we get what? We get e to the I n theta is equal to e to the I phi. What does that mean? It doesn't mean they're equal, right? It means that, therefore, phi minus n theta is equal to 2 pi I times, let's say, k for some k in the integers, rather, right? So in fact, we can write down a formula for the nth roots of w, right? So we see, like, basically, let me kind of recap our goal here, because I know it's just like 4 letters you don't understand, right? But there's 2 letters we're interested in terms of the others, right? We'd like to express this in terms of given rho and phi, right? I mean, I could be even more, I could be less ambiguous. I could insist that phi be the principal argument of w if I wanted, right? I haven't specified. Phi is just an element of the argument of w at the moment. But we could be more specific. But I won't at the moment. So what is w to the 1 over n? It is equal to my z. So solve this for r. What do you get? R is equal, should be, bless you, nth root. Nth root of, I'm remembering a joke. I can't remember what the joke was. Nth root of rho, that's my magnitude. The nth root of rho. Okay? And we should understand this is the real nth root, as in like pre-calculus nth root. It's the, if n is even, it's the positive number whose nth power gives you back rho. And if n is odd, it's just the nth power gives you back rho. You know, when n is even, we have to make a choice, you know, for the real root. You know what I'm talking about? No? Okay. Fourth root of 16 is 2, even though minus 2 to the fourth is equal to 16. By definition, it's the positive root in the real case. There's no issue with an odd power because, like, you can take, you know, the cube root of, you know, 8 is 2, and the cube root of minus 8 is minus 2. Anyway, I'm getting off track here. My point to you is we already know about nth roots from pre-calculus. Let's not reinvent the wheel. So anyway, so that's the nth root. And then what's phi? Well, I don't want to find phi. I want to solve for theta, right? So theta here is equal to what? Looks like we've got ourselves a phi minus 2 pi. You know what I'm going to do? Sorry about that. I'm going to say that this was n theta minus phi. It doesn't really matter. But that'll not put a minus in my formula. My apologies. I flipped the sign on that. So then solving for theta, I've got phi plus 2 pi I k divided by n. That's my theta. So I have the nth root is e to the I times phi plus 2 pi I k over n, such that k is an integer. That's the nth roots of w. Now let me kind of unravel that. Let's set phi equal to the argument of w. Then we have the following formula. The nth roots of w are apparently the nth root of the modulus of w times e to the I, what is it? Arg w divided by n times e to the, well, let's see here, 2 pi I over n to the power k. Now I did make a slight adjustment in the formula here. What I did was I used the adding angles formula for the exponential, and I kept the part with phi separate, and then I peeled off the other piece. And there's no I in here. This is a mistake, right, guys? Look at this. This I is not here. Poke this I out. There you go. Better. Only one I. Yeah. Yeah. Much power in the eyes. Let's see here. Okay, so I just set phi to be the principal argument because I can, and then I have this. Now the quantity I have right here, e to the 2 pi I over n. This is a special thing. This right here is a principal nth root of unity. Notice that and we'll call it omega sub n, all right? Notice that like omega sub n to the nth power is equal to e to the 2 pi I over n to the nth power, which is e to the 2 pi I, because n over n cancels. And what's e to the 2 pi I? One, right. So do you see why we call this a principal nth root of unity? See, because omega n is an element of the nth roots of 1. It is a nth root of unity. Of course, any power of omega sub n is also a solution to the equation something to the nth power equal to 1, right? So, in fact, omega sub n to the power k is an element of this guy for any k in z, right? So the nth roots of w are actually given to us by calculating one thing and then just multiplying by principal roots of unity. Powers of that, actually. So like, let me write it out a little bit more explicitly. What we got here, if I make a list, is the nth root of w, nth root of the modulus of w. And then I'm going to start us. This is, what choice of k for that? Ooh, my bad. I'm sorry, guys. I forgot my e to the I arg w over n. Next up, nth root modulus of w, e to the I arg w over n, now times omega sub n. So just to recap what I'm doing here, you're looking at k equals to 0 for the first term, k equals to 1 for the second term, all right, 0 of them, 1 of them, and then it's squared, then it's cubed. See, this part stays the same. The k dependence is only appearing here, right? So this goes on. Next one is the nth root of w, nth root of the modulus of w, e to the I arg w over n times omega sub n squared, and so forth and so on, dot, 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 until we get to the nth root of the modulus of w, e to the I arg w over n, omega sub n to the n minus 1. And that's actually it. I haven't proved it, but it's true. The nth roots of unity, there are only n nth roots of unity. I can prove it by the fundamental theorem of algebra. Maybe we should do that. Now here, you notice we keep writing the same expression over and over and over again in this list? There's like a cleaner way to write this. Definition. The nth root of w is equal to the nth root of the modulus of w times e to the I arg w over n. This is the principal nth root of w. So if you look at it, we wrote that every single time. So another way I could say this is to find the set of nth roots of w. Just to recap here, the nth roots of w have the form the principal nth root, and then we take the principal nth root, we multiply it by the nth root of unity. We take the principal nth root of w. We multiply by the nth root of unity squared, and so forth and so on, until finally we get to the nth root of w, modulus w, times the nth root of the modulus. Oh, I'm an idiot. Sorry. Give me a second here. It's fine, it's fine, it's fine. The nth root of w to the n minus 1. And if I had to do it over again, I would label the principal roots of unity something other than omega when I'm using the w here. I'm sorry. It just happened. If it bothers you, you can use a different notation for the nth root of unity. Like some people use this thing for the nth root of unity. Books vary. Okay? Now, I'm going to prove that there are just n roots of unity in a second here, but before we do that, let's stop and appreciate what they are. Oh, yeah? Let's appreciate what they are before I show you why there's only n of them. Ooh, I shouldn't have done that. It's already done. I was gonna, we could define instead of the principal root. So I'll just say it in words. It's in the notes. We could also define instead of the principal root of w, we could define like an alpha root of w. And the way we do that is instead of putting the principal argument here, if we put like args of alpha, then I call it like the alpha root of w. And I have like an upper and a lower root. I have horrible notation to make this explicit in the notes. No one uses this notation. There exist problems where that notation would be helpful. I don't know if I've assigned them for you this semester, but I'm just saying it's something that notationally I've been at an impasse before. That's why I made up those notations. The larger point here is that there's more than one way to take a root of a complex number, right? Because there's many choices for the angle. All right, let's just roots of unity. Let's get it out there. Well, this is dead. Too low. So omega sub 1, e to the 2 pi I over 1, also known as 1. So the first root of 1 is just 1. And
is that omega over there like omega squared? That's not w? Right? Is that what you were just saying?
yes,
Oh, okay.
my w's are pointy. My omegas are not,
Okay.
except when they are.
Sorry.
I know. Well, this is what I was trying to warn. If you want to, I can start putting some hats on the omegas.
There we go.
Anyway, okay, so first roots of unity, not really that interesting. No one talks about this. How about omega sub 2? E to the pi I, 2 pi I over 2, which is e to the pi I. So the principal second root of unity is minus 1. So this means that if we look at the, what are the second roots of 1? You got 1 and you got minus 1. That's it. On the other hand, omega 3 is e to the 2 pi I over 3, also known as cosine 2 pi over 3 plus I sine 2 pi over 3, which we could figure out if we do some trigonometry. It's like over here, right? So this is pi over 3 that's left to get to there, which means that we're looking at what? Cosine pi over 3 is what? No one knows what cosine pi over 3 is? Is this what's become of the math major now? Too good to know what cosine of pi over 3 is, are we? No? Was that a square root of 3 over 2? It's a good guess, but I think it's a half. Now, but the thing is, but that's just like the reference angle. So we need to put a minus, But I wasn't asking you that, so I was looking for a half. But now what you said is this guy. So plus I squared 3 over 2. So
For the second omega, is it supposed to be 2 pi I over 2?
yeah,
Equal to-
yeah, 2 pi I over 2. Remember, the definition is that omega sub n is e to the 2 pi I over n. So this is omega sub 3, right? And then down here, you've got omega sub 3 squared at 4 pi over 3. 4 pi over 3 there. And then, of course, we also have this one, 1. 1 cubed is 1. So you see the third roots of unity are these guys, you know, minus 1/2 plus I root 3 over 2, minus 1/2 minus I root 3 over 2, and 1. But I prefer to write them omega sub 3, omega sub 3 squared, and 1. Did I do something? Violet looks perturbed. Oh, okay. All right. Omega sub 4. E to the 2 pi I over 4, which is e to the pi I over 2, which we talked about a second ago. That's I. The fourth root of unity is I itself. And so if I do the fourth roots of 1, I got a 1, an I squared, and I cubed. And that's it. I to the fourth, of course, is 1 again. So the fourth roots of unity are explicitly 1, I, minus 1, and minus I. These are the fourth roots of unity. Are we good? Now you might wonder what we can do with them. I'll show you. So let me, it's just interesting to plot these two, right? You see what's going on here? I minus, so there's like I minus 1 minus I and 1. Notice how they're like perfectly symmetrically situated around the origin.
They're all separated by 2 pi over n.
Yeah, exactly. Same here, right? And it was still true in these two cases, but in a kind of silly way. All right, so think about this. If we look at the polynomial f of z equals z to the n minus 1, then if, if z, let's say z sub k is an element of the the nth roots of unity, then what? Z to the k, z sub k to the nth power is equal to 1 by definition, right? Thus, f of zk is equal to what? Zk to the n minus 1, 1 minus 1, 0, right? In other words, any such z sub k is a 0 of this polynomial. Agree? What is it? Did they say something? No? So we know the factor theorem, right? What does the factor theorem say? So that implies that z minus zk is factor of f of z, right? So I can start writing it like this, right? F of z is apparently equal to z minus z1, z minus, okay, get started 0, z minus z0, z minus z1, z minus z2. I guess if I start at 1, it's more natural. I'm sorry, I'll make up my mind eventually. And this can't go past what? I mean, it has to just get to there. Why? Now I'm assuming that these are distinct nth roots of unity, right? And assuming they're distinct nth roots of unity, I get a new factor each time. Like if the roots were repeated, then I wouldn't get a new factor. You know, it would already be 0 because of the factor I already had. But if I assume that these roots are distinct, then every time I get a new distinct root, I get a new distinct factor. Right? Because if these numbers are different, there's no way you can rewrite one of these as the other. So what would happen if there were more than n roots of unity?
Wouldn't Z have a power greater than n?
That's right. You'd have a factorization of an nth order polynomial with more than n linear factors, which is clearly absurd, because if you multiplied them out, you'd have a leading power which is larger than z to the n, which is of course absurd. So there cannot be more than n distinct roots of unity because of this argument. This does not prove that there exist n distinct roots of unity, but that's also fairly clear from the formulas I wrote on the board. Essentially because of the geometry of the problem, which is that the nth roots of unity are obtained explicitly by what you said. We start at, you know, this angle, which is theta equals to 2 pi over n, right? And then you've got one, and another, 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 until you get around to 1, right? And so if you take 2 pi and you divide it by n, I mean, you divide 2 pi up into 2 pi over n wedges, you get n wedges, which correspond to the nth roots of unity.
So why does Z sub k to the n have to be 1 for any element n? 1 and 1 over n.
That's the definition of z sub k being in here, is that this nth power of that is 1. That was our definition of 1 to the 1 over n. Right here. So w to the 1 over n, it's the set of all z such that z to the n is w. So when I say that z sub k is in an nth root of 1, that means that the nth power of zk, it has to be 1. I am making a distinction between things which you have confused in the past, right? You were taught in pre-calculus that the square root of 3 is equal to 3 to the 1/2. This is no longer true. This is not the case.
Work for the complex numbers.
No. Well, let me show you something. Let me show you something on the projector, because I always, if I try to write this out, I'll mess it up. But I have it in the notes, so I'll show you the notes. I have a hard time like getting confused, like showing a wrong calculation. It's not really a wrong calculation, but like showing a confusing calculation. I sometimes have a trouble like getting to the confusion, you know? Let's see here. So if I can find it. I was reading it before class. Come on. All right, well, hey, come on, wake up, punk. Well, this isn't what I want to show you yet, but this is worth looking at, well, since we're here. So, like, look at, so these are the fifth roots of -1. All right. So the principal fifth, so like -1, remember the principal argument was what? Pi. It's over there. Well, it was over there. I erased it. Start of class, we talked about this. The principal argument of -1 is pi. So if I take principal argument, divide by 5, this right here is the principal fifth root of minus 1. Then I take that and I multiply by e to the 2 pi I over 5, because that's omega sub 5. So each time I add 2 pi I over 2 pi over 5. So then I go to 3 to 5 to 7 to 9. That's it. Now these are, again, if I were to draw these, I don't think I have a picture in the notes, but I'll draw them up here. They're not, so like the principal roots of unity, they're situated, there's always like the number 1 in there. So here, minus 1, the principal fifth root of minus 1, e to the pi I over 5, e to the I pi over 5, yeah. It's a fifth of the way from here to here, so it's like here-ish, right? So that's e to the pi I over 5, pi I over 5. And then 2 pi, that's like, what's the next one? 3 pi? 3 fifths, that's like 0.6 of the way. So that's like here-ish. And then I've got what, 7 over 5, that's like 1.4 pies. So the same amount of this, it's like, I don't know, I'm not, I'm very bad at, I'm trying to take this circle and divide it up into 5 equal wedges, you know? So that's like what degrees? What's 180 divided by 5? That maybe would help me. 36, that's kind of right. So then I want to go 3 times 36, which is what, like, so that's more like here, right? And then, wait a minute. I'm sorry, guys.
Would it be 360 divided by 5?
Yeah.
Oh,
So 72 each time.
72 each time? Oh, so it was, oh man. This is not interesting. I'm sorry, guys. So here-ish, here-ish. Where's that 9 pi over 5? Oh, okay. Oh, so one like up here, one like down here, one here, one there. And where's the fifth one? Minus 1? There's 5. Oh, seriously?
It'd be, I think, 288 degrees.
Well, there's minus 1 itself, right? So minus 1 is, of course, here. This feels wrong.
You need to move the 1 and 1.
I think it was supposed to be more like this.
Yeah.
Something like, they should be symmetrical. Listen, the thing is, there's some interesting patterns here, right? So these are the, you know, minus 1, the fifth roots of minus 1 are these guys. Okay. Now, if this is a real number, then the roots, they come in like conjugate pairs. That has to happen because remember that this plays into the factorization of, you know, that comes from z to the fifth equal to minus 1, which gives us z to the fifth plus 1 equal to 0, right? So if you think about that polynomial, every one of these is a 0 for it, which is what I have, that factorization right there. So there's this really neat interplay between, you know, like how we can find the principal nth roots of unity and how we can factor polynomials. See, you can factor, well, you can factor a lot here, right? Think about it. I will get back to your question about the half in a second here.
And it'd probably be, it's probably the unit circle just because we have magnitude 1.
Right. Exactly. But here's a kind of here's an interesting quote. This is from Galois. He says, "Go to the roots of these calculations, group the operations, then classify according to their complexities rather than their appearances. This, I believe, is the mission of future mathematicians. This is the road in which I am embarking in this work." So, this is one of the main sort of fathers of group theory, although he died at like 20 or something, yeah, in a duel, probably over a lady or politics. I don't know, but there's a great song about it. But I'm not sure I dislike you guys enough to make you listen to it. But anyway, so that's exactly the sort of the foundation of Galois theory, is this insight that different roots to a polynomial could be related by like a rotation. See, because the different roots to this z to the 5th plus 1, they're all related by just taking one root and rotating to another. So if you can abstract that idea, that's sort of the core idea of Galois theory, which is something that I think Dr. Sperano might offer a class in. All right, so here, it's hidden in the next chapter, but this is the calculation I want to show you guys. So let me show you the trouble of the regular exponential notation. 1 is minus I squared, but that is minus I times I, which is, of course, I is the square root of minus 1, right? Well, it's minus 1 to the 1/2, yeah? Okay, great. So then that, and then of course the product of the square roots is the square root of the product. Everybody knows it. And so you just do that. And then of course minus 1 times 1 is minus 1 times is 1. So then we have minus out here still. And then, what's the square root of 1 is just 1. So we got minus 1. Oops. So this is the problem. Now, this calculation is repaired if instead of working with a single square root, we work with the set of square roots. See, because like 1/2, 1 to the 1/2 is actually 1 and minus 1. It's a fortunate event that the quadratic formula as we know it works. Like, you have the square root of the discriminant,
Yeah.
and we put plus or minus there. It's still true in the it's still true in the complex case, because plus or minus is multiplication by omega sub 2, or not. So like, but that square root of the discriminant must be understood to be the principal square root, which involves complex calculation. If the thing underneath the b squared minus 4ac is actually, if it's complex a, b, c, that formula still makes sense, it turns out. But we have to calculate the square root of b squared minus 4ac using the definition that I just put down over here. And proving that that formula still works is a homework problem I sometimes assign in here. And invariably I get students who just quote back to me, "What's the quadratic formula?" I'm like, yeah, I know. Why is it true? So, all right. I think that's pretty much it for chapter 1, guys. So let's forge. I mean, there's more examples in chapter 1. Like we could, since I got this thing out, we could look at another one while I got this open. Check this out. So if we have 3 plus 3i, the magnitude of that is the square root of 3 squared plus 3 squared, which is the square root of 18. So magnitude of 3 plus 3i is square root of 18. The argument of this, since it's going 1 over and 1 up, 1 plus I is at 45 degrees, that's pi over 4. Principal argument is at pi over 4 for 3 plus 3i. So I can see that that's pi over 4. And of course, here's the polar decomposition. 3 plus 3i is equal to the square root of 18 times e to the pi over 4. Great. Now if I calculate the 4th root of the magnitude, I get the 8th root of 18. Watch out for me. Sometimes when I'm doing calculations, I'll forget to put the square root from the magnitude. So if you're looking at my solutions, if something seems amiss, it probably is. I make mistakes. So ask me. But anyway, I did it right here. This is the kind of like spiel I make right before I make a really dumb mistake, so I gotta be especially wary right now. God has a sense of humor. Pride to go before the fall. So the fourth root of the square root is the eighth root. Yeah. And so this is the fourth root of the modulus of 3 plus 3i. And then why is there I pi over 16? Well, we take what? We take the principal argument and we divide by 4 if we're calculating the fourth roots. So I start with pi over 4, divide by 4, I get a 16th. And then what happens is to get to the next one, I multiply by the fourth root of unity, the fourth root of unity squared, the fourth root of unity cubed. See, finding principal fourth roots is pretty easy because you just multiply by I squared, I cubed, and starting with the principal fourth root. So yeah. All right, so then let's start chapter 2 here. Chapter 2 is on functions of a complex variable. And I think it's worth our time to take a second to read a quote, a little bit of history. So Leibniz is often credited with the the origination of the term function, and it's probably true, I suppose. Euler essentially defined a function by its formula, but later Euler did discuss the idea of an arbitrary function in his study of variational calculus, of which he's one of the fathers of, right? You talk about the Euler-Lagrange equations, it's that Euler. Euler had his hands on everything. But Dirichlet said the following. He said, it's certainly not necessary that the law of dependence of f of x on x be the same throughout the interval. In fact, one not even need think of the dependence as given by an explicit mathematical operations. This is the modern view of functions, that a function is not defined by its formula alone, that you see we have to give both a rule and a set on which the domain defines, and also a codomain where the values are happening, But like 19th century mathematicians, much like students, like to think of a function by a formula, right? But we've only fairly recently grown past thinking of a function just by its formula. So anyway. I got that quote from, I think, Ramire. The more interesting quotes in this are typically from Ramire's work. So there's three main questions that are going to guide our investigations in this chapter, all right? So if we have a function of a complex variable, all right? So it's defined in some subset of the complexes and its output is complex, then our typical notation is to write f equals to u plus iv. Here, u and v are understood to be real valued functions of s. So this is the real part, this is the imaginary part of the function f. So we're like the real part of f of z is this, the imaginary part of f of z is that. And we say that u is the real component function, v is the imaginary component function, and collectively we'll refer to u and v as the component functions, all right? So that's one of our first orders of business, is given a complex function, find the component functions. I'll actually show you those in a minute or two. I just want to read through these things. If I wrote them out on the board, we wouldn't get anything out of it. And it's just better to look at the projector for this. So, and another important question is, for a given complex function, what's the modulus of the function? What are the possible outputs, the size, the magnitude of the outputs? And so that's going to be judged by the square root of the sum of the squares of the real and the imaginary components. Yeah. So that's sometimes useful and important to look at. I wouldn't, it's sort of secondary importance to just finding u and v, honestly. And then finally, we're interested in the question of invertibility. This is by far the most sophisticated question I've raised so far, is if we're given a function that's defined by a subset of the complexes, how can we find a suitable inverse function for f? Is it possible to invert a complex function? And we'll see that this is a pretty challenging question. A lot of times what we'll find is that in order to invert a complex function, we have to take the domain which is given and we have to restrict it. You've already seen this idea in calculus. You talk about inverse sine, inverse cosine, inverse tangent. But sine, cosine, and tangent are not one-to-one, right? They fail the horizontal line test infinitely many times. For a function to be one-to-one, for a function to be invertible, it has to be a one-to-one function. Otherwise,